Good afternoon, everybody. Before start, we have an announcement. At 4:30 p.m. in MWT2, there is a lightning talk. If you are interested in this talk, just feel free to join and listen to some participants. Coming up next, we have Michaelis Papas, and he will talking about beyond software defenses, hardware assists CFI on ARM-based system. Just give him a big hand.
Thank you. Okay, so hi everyone. Thank you for joining this talk. My name is Michaelis. I'm a staff engineer at Unicraft. Unicraft is an open source unikernel operating system that I regularly contribute to and also co-maintain with others. And Unicraft GmbH is a startup that uses Unicraft to provide cloud services. So my motivation for this talk is the work that I did to provide hardware-assisted CFI for Unicraft and ARM64. So this is the result of my work and the knowledge that I obtained by going through that. So what is control flow integrity, first of all? So most software attacks rely on subverting the execution path to malicious code, right? So by control flow integrity, we refer to a set of security techniques that actually try to limit or restrict the code execution flow to the intended execution path. So let's have a brief overview of CFI attacks and the mitigations and how they evolved over time. So during the 90s, buffer overflows were the big thing, right? So I think you all know how these things work. If you can overwrite the buffer in the stack, then you can write your malicious code there, and then you can also overwrite the return address to point to your malicious code, and then it's game over, right? And from that point on, a cat and mouse game starts, where people start introducing mitigations, and of course, researchers start demonstrating ways to bypass them. So the immediate response to buffer overflows was the non-executable stack, right? So mapping the stack as non-executable now prevents the attacker from executing their malicious code, so they can write still on the stack, but they can no longer execute there. And of course, right after, people demonstrated ways to work around this. So the first code reuse attack was demonstrated by Solar Designer. It was a return to libc, so now instead of executing your own code, you return to execute the existing code in the standard library. Meanwhile, other defenses were introduced, like stack guard and stack shield. These are stack canaries and shadow stack, or ASLR, where the virtual address space is randomized and then the attacker doesn't know in which address to return. So, of course, in every single time, people demonstrated ways to bypass these protections. So, at this point, the CPU vendors started introducing dedicated countermeasure for software attacks, and most famously the non-execute bit. And with that, what actually happens is that you can have memory either writable or executable, but never both, right? And this is the end of, let's say, puts an end of the possibility for attackers to execute code that they have provided, they have written in memory, right? And at this moment, of course, the focus from the attacker's side goes into code reuse attacks, and this is when return-oriented programming and jump-oriented programming and all these techniques become popular. I will not go into much detail about how these work. What you need to know is that instead of writing your own malicious code into memory, what you do instead is that you find small chunks of this code into the existing program, right? And these are called gadgets. And then you somehow get the execution to execute these gadgets one by one. So little by little, you eventually get to execute your malicious code via existing code and not by code you have supplied into memory. The problem with return-oriented programming and jump-oriented programming and all these techniques is that it's very hard to defend against with software, right? So these have become very, very successful attacks. And of course, at this point, CPU vendors start looking into hardware-assisted mitigations. And this is what we're going to be looking at today. So we will focus at ARM, and specifically Pointer Authentication and BTI. But before we get there, we need to define our threat model. Pay attention to this because this is very important. Our assumptions here is that the attacker has obtained read primitives and write primitives, so they can read and write into arbitrary addresses in memory, and they are trying to obtain arbitrary execution. The other very important assumption is that, of course, a non-executable stack is in place, because if you don't have that, then you fall back into traditional buffer overflows, right? So let's start with pointer authentication. So pointer authentication is a mandatory extension in ARM v8.3 and ARM v8.6. So as the name implies, it relies on authenticating pointers. So of course, there is a cryptographic operation to sign the pointers first, and then another one to authenticate them. And how it works is that you start off with, of course, the pointer that you need to sign. The pointer has some upper bits that are unused or almost unused. We will see exactly in detail why that happens. And then you have, of course, a secret key, and then you have also an additional modifier value. You pass the address to the cipher algorithm, and then the output of the cipher algorithm is XORed with the upper bits, and that forms the signature. This is called the pointer authentication code. This now replaces the upper bits, and now you have the signed pointer, which consists the signature and the address. So let's look in more detail about the upper bits. So first of all, why do we have upper bits in the first place, right? So in 64-bit systems, pointers are not 64 bits wide. The pointer size is configurable. In Linux, the default is 48 bits, but you can configure the size of the virtual address to be between 30-something up to 50-something bits. Let's stick to 48 bits now because this is the default, but you can imagine that this can vary, right? So what can go into the signature you see here is what you see there as extend bits. I will not explain in detail what these are, but just keep in mind that the signature of the pointer can go into these yellow blocks, the extend bits. Sometimes, if you have other features implemented, like what you see there, MTE or BTI, again, I will not explain what these are, but you can keep in mind that other security countermeasures or other features can reserve some of these extended bits. And then this means that you have less bits for the signature, right? Yeah, that's it for now. So, how about the key? So, the ARM specifies that you have 5 different keys. You have 2 keys for signing instructions, instruction key A and instruction key B. You have 2 keys for signing data and 1 key for generic purposes. And it is down to the operating system or the compiler to decide how to use this. So you can imagine, I don't know, theoretically, that you have an operating system that uses key A for its own purposes, for the kernel, and then uses key B for the user space or whatnot, right? It is really implementation defined. The modifier, you might wonder what it is about, because normally you would only need, let's say, a pointer and the key, right, to sign. So the modifier is very important because it puts some context and avoids a certain type of attack where an attacker can substitute one signed pointer with the other. But if you use a modifier, then you limit a signed pointer to a given context. And The most common use is to use the stack pointer for that. So then you say, I sign the return address with the given key for this particular value of the stack pointer. So now the sign pointer is also limited to this particular context, right? So changing the value of the modifier, of course, will result in a different signature. Okay, so the cipher. So the reference cipher is called Karma, and it is designed by Qualcomm and ARM. So it's a block cipher like AES, which means that it operates on blocks of fixed size. It's called a lightweight tweakable block cipher. Lightweight because, as opposed to AES or similar block ciphers, it provides just acceptable security for a given purpose, right? It's a purpose-designed algorithm, and therefore the security has to be good enough for the purpose. Unlike generic block ciphers like AES, that they have to have like, I don't know, full security or as good security as possible. And tweakable means that you have this additional modifier parameter. In point authentication specifically, you have two variants, Karma 5 and Karma 3. Karma 5 has 5 encryption rounds. Karma 3 has only 3 rounds, which means that it sacrifices a bit of security for performance. All the implementations, all the reference designs from ARM that I've seen, they use Karma 5. You can also have an implementation defined algorithm, and this is exactly what Apple does on the M series, right? They use their own algorithm, they don't use Karma. Okay, and of course the opposite operation, the authentication, you start with your authenticated pointer. You pass the address part again through the cipher with the same secret key and the same modifier. Just for reference, the modifier is not secret, right? And the result of that, you XOR it with the existing point authentication code. If everything goes well, then you end up with the upper bits that you had before, and then your pointer is authenticated. If something goes wrong, which means that if your, I don't know, pointer was modified or something like that, you will end up with an abort. Okay, so moving on to the implementation, ARM has added new instructions into the instruction set. There are two big, let's say, classes of instructions, the basic instructions and the combined instructions. The basic instructions provide instructions for authenticating, for signing a pointer, authenticating, or stripping the signature from a pointer. And it's 32 of them because although there are essentially 3 operations, you have all the variants, right? So you say, I have one instruction to authenticate a pointer with instruction key A and modifier, I don't know, the stack pointer. You have another instruction to do the same thing but instruction key B, right? And for other modifiers and so on and so forth. But in practice you have these 3 operations. These are implemented in the processor's hint space, which means that for if you execute these instructions into an older processor, the processor will execute this as an op, so nothing will happen, right? Your code will keep executing, of course it will not be protected, but it will be backwards compatible. The combined set essentially does the same things, but with additional operations. It's, let's say, a convenience, so you can have authenticated return. Rather than doing first the authenticate and then the return, you can do both in one instruction. You can do other things like authenticated branching, right? If you need to jump from one part of the code to the other, you can do it in an authenticated way. Authenticated loads, and so on. These, unlike the basic set, are fused instructions, which means that they are either supported by the processor or you get an abort. So if you try to execute code with these instructions into an older chip, it will just not work, right? You get an abort there. So this is how it looks like. You can see on the left side, you can see a function protected with point authentication with the basic set, and on the right, you can see the combined set. So how this starts, first of all, this is to protect the return address, right? And the first thing that happens is that you sign the return address with instruction key A. You see this IA part in the instruction, and with modifier, the stack pointer. Then, of course, the function executes as normal, and before you exit the function, you authenticate the return address, and then you do the return. The only difference with the combined set on the right is that the authentication and the return happen in one combined instruction. Of course, the other difference is that the basic set is, as I said, backwards compatible with older chips, right? The right one is not. So that's it, more or less, with pointer authentication. Of course, there's much more there, but at least these are the basics. So let's look at BTI. Well, I'll drink some tea first. Okay, BTI is again a control flow integrity measure. It's a little bit different than point authentication. BTI is also a mandatory feature, which means that from some point on, it will be available on every processor. And it mitigates against indirect jumps. What is an indirect jump? Let's start with what is a direct jump. So when you need to jump into different parts of the code, with direct jumps, the compiler knows where you want to jump, and then the instruction that does a jump is relative to the current instruction plus minus an offset. These are not vulnerable, right? Because the instruction literally looks like jump plus, I don't know, that many bytes, right? Indirect jumps, however, are a bit different because the jump happens, is based on the value of a register. And this means that this is vulnerable to attacks because if the attacker can manipulate the register, then they break the control flow path to jump to wherever they like, right? And this makes it capable for these jump-oriented programming attacks and so on. So, how BTI looks like. When we compile code with BTI support, the compiler tries to find what are the possible places that indirect branches will jump to. So let's say the branch target, and we'll add this BTI instruction there. So if any code jumps into any other instruction that is not BTI, an abort will be generated. And that ensures that all jumps happen at legitimate instructions and not to attacker-controlled instructions, right? Or at least that's the idea behind BTI. So how is this implemented? First of all, yeah, as you saw, there is this BTI instruction that is new in the instruction set, and it also has a type. The type encodes the type of the branch, and this is similar to the modifier, right? It tries to restrict further the origin of the jump, right? So you have, I don't know, type for calls or type for jumps, or some types can be, some jump targets can be legitimate for both, and so on, right? So you still try to restrict a little bit the origin of the jump. And as far as backwards compatibility is concerned, BTI instructions are also implemented in the hint space, which means that again, code compiled with BTI running on older chips will still work, but of course without the protections. In addition to the BTI instruction, there is also a page table attribute called guarded page. So when you create your page tables, if you map a page and mark it as guarded page, then it will be protected with BTI. Any pages that don't have this guarded page attribute enabled, then they are not protected by BTI, and then BTI instructions there will be ignored. And this allows again for backward compatibility and so on and so forth. Finally, we have some bits in the process state. So the process state is a register that holds bits related to the execution state. So what you know for sure is these bits that are the condition flags that say, I don't know, the carry flag, the zero flag, the overflow flag, that show what happened after an arithmetic operation in the processor, right? BTI introduces additional bits for branch type into the processor state, and these encode the type of a branch. So bit type is updated on every instruction. So if one instruction is not a branch, then the bit type bits will be 0. If it is a indirect call, it will have a value. If it is an indirect jump, it will have a different value, and so on. And this means that actually when you do a jump, it's not only enough to jump to a BTI instruction, but also the BTI instructions have to match the value of the bit type, right? So as I said, this is similar to the modifier. It restricts your jump targets to specific origins. Okay, so now that we have all the background, let's see what is the current state of support in the ecosystem. So first of all, both GCC and CLang support both Pointer Authentication and BTI. They use the same flag called the branch protection to control these features. You can choose if you want any of them, whether you want Pointer Authentication or BTI, or both, and so on. However, the compiler support for both GCC and CLang is pretty basic. So, especially Pointer Authentication only protects the return address. So you don't have, as you noticed earlier, there are also instructions for protecting, let's say, do authenticated load, right, or authenticated jumps. GCC and CLang do not support this. So, for example, the C++ vtables are not protected, right, and so on. The idea, I think, is that for these things you rely on BTI. However, Apple uses their own fork of CLang, right, and Apple has a much more complete support for Pointer Authentication. There is an interesting paper that goes into a lot of detail for Apple's implementation, and I think it's a very good read for that. Okay, operating system support. We will focus, of course, on Linux and Android. So first of all, there are options to enable or disable these features, both for the kernel and for user space, or for either. For the user space, you have keys generated, separate keys for every process, which means that when the kernel does the context switch from one process to the other, it has also to switch the keys because they are stored in registers. And within a process, the same keys are shared between threads. When a process does a fork, the keys persist, and they are only updated when the process does exec v to switch to a different process. On the kernel side, you only have the instruction key A, and because also user-based processes, of course, use instruction key A among all the others, the kernel has to update the key upon kernel entry and kernel exit to its own key. Once again, Apple has a much more complete implementation, so it will be interesting to have a look there. Okay, hardware support. You will see that both features are becoming now ubiquitous in all type of major ARM processors. So you can see system-on-chip design for the cloud, like the Graviton, or for desktop and all the major mobile vendors. Eventually, they support more or less both. And time to go for evaluation. I think this is the most interesting part. So, how secure are they? Of course, the probability for a successful brute force depends on the number of bits of the signature, right? And this table shows the probability for different virtual address size with the various other features that reserve some of these extension bits enabled or disabled, right? So you can see for 27 bits, the probability for a successful brute force is very, very low. The worst case, of course, is 52 bits with 3 signature bits. This is pretty uncommon, right? The 48 bits is much more common. So you have there probability 1 over 128. However, what is important here is that the first time when you do a brute force, you fail, then you get either application crash or kernel crash, right? Because you get the abort, which means that you cannot do like brute force, right? You fail once, you're done. Then either that the process is restarted or the kernel is restarted, then you get new keys generated, you start from 0. So brute force is not an option there. Also notice that pointer authentication is not vulnerable to information disclosure like ASLR, right? The keys are stored into registers. They are not stored into memory. Remember the threat model, right? The threat model said that the attacker has arbitrary read, arbitrary write, and is trying to get arbitrary execute. However, the keys are in registers, and to read the registers, you do it via special instructions, which means that you need execute path, which you don't have, right? So information disclosure is not the case here. For BTI, you have, let's say you have an object with a number of BTI instructions, and you want to have a chain, to find a chain of n gadgets, right? And if we assume that the number of indirect jumps in a given object is around 1%, then the probability to find a certain number of gadgets approaches 0 as the number of gadgets grows, right? So again, at least the theory is very much in favor of the defenders. Okay, how effective is this? So ARM has various white papers where they claim things like, I don't know, 50, 60% improvement, 70% improvement, but they don't provide enough information to reproduce their numbers. And I was quite annoyed by that, so I thought I should do this myself, because you should not trust, especially the vendor that advertises something. So I took Unicraft because this is the operating system I'm familiar with. I did this work for Unicraft, right? So I thought that I should benchmark with Unicraft also because it's pretty small and so on, right? So I took Unicraft and I compiled it for Nginx. And then I used Rob Gadget, which is the de facto tool for finding these small chunks of code called gadgets to see actually what is the effect of ARM's protections, right? So with no protections, I found around 40,000 unique gadgets. Then with pointer authentication, it's the same. I excluded all the authenticated returns, because then these gadgets are no longer valid because they're protected. And I ended up with around 3,000 unique gadgets. So this is a huge improvement, right? The number of gadgets was reduced by more than 90% with pointer authentication. And of course, this is only for return-oriented programming because, as I said, GCC and CLang for Linux only protect against ROP, right? Now, you will say, okay, why 92% and not 100%, right? Where's the other 8%? And I started decompiling code and looking, and then I found a common pattern in both GCC and CLang that you'll see here that the red part is not protected, right? The protected code starts after that. And I'm not a compiler engineer, and I have no idea why, but given that this pattern is common in both GCC and CLang, it might have to do with how the compiler, I don't know, processes with different iterations the code, or generates it with different iterations. These parts of unprotected code, though, are very small chunks that do something like, very simple, like check a function parameter on entry, and then if it's, I don't know, invalid, just return, you know, throw an error, something like that. So this is an open question for me, so if anyone has any idea, I would be very interested to know why. I'm even tempted to open a back report in GCC and CLang and see what actually the compiler engineers say about that, because it's very, very interesting. Okay, so I did the same for BTI. defining job gadgets, it's a little bit more tricky than ROP gadgets, but it's not also that hard. So when we say depth, we mean a certain number of instructions. So the depth of a gadget is, let's say you want your gadget to consist of, I don't know, 3 instructions or 5 instructions, right? Essentially, a job gadget is depth number of instructions until an indirect jump. So I patched ROP gadget to remove return because I assume that return is already protected by Pointer Authentication, and I ended up with 8,000 unique gadgets. Yeah, okay, this is my patch for removing the return, just for full disclosure of my methodology. And then I enable BTI, and then I want now to find also how many gadgets are left with BTI enabled. So how do I define now a job gadget with BTI enabled? It is again a certain number of instructions that end up with an indirect branch, but they also have to start with a BTI instruction, because I cannot jump to anything else other than BTI, right? So, of course, ROP gadget again did not support this. It doesn't know anything about BTI, so I had to come up with some post-filtering ideas. So you can see this command line there, that I had to come up to filter out what I wanted to find. But either way, I ended up with 48 unique gadgets. So from, where was that? 8,000, right? You end up in 48. And in practice, this is even smaller, because I don't take even into account the branch type here, right? So it's even less. So this is more than 99% improvement, which is, again, it's great, right? Okay, so performance. What is the overhead of these things? So for Pointer Authentication, you have one instruction at the end of the function and one at the return, assuming the combined set. So you have +2 instructions per function. If we look at the optimization guide of Neoverse, which is one of the reference designs of ARM for cloud, you can see that the authenticate takes 5 cycles, and the authenticated return, the sign takes 5 cycles, and the authenticated return takes another 5 cycles. So in practice, we have +10 cycles per function. 10 cycles are, I don't know, 5 multiplications, right? It's okay. It's not so big, right? It's not negligible, but it's still not so big. For BTI, things are much simpler, right? You have only +1 instruction per indirect branch. And although in the optimization guide, I looked at all of the ones that I could find, they don't document it. I think it's safe to assume that it's only one cycle there, because it just does one check against the processor state branch type. So this is one cycle per indirect branch, and if we stick to the assumption that indirect branches are 1% of the total instructions, then again, this is nothing. Of course, I wanted to still take some measurements in practice, so I compiled Unicraft for the nbench byte benchmark, which is very common benchmark that people use in the papers and so on. And also I did the same for NGINX using the WRK stressing tool to see, measure the request per second and the transfer per second and so on. And I executed this with QEMU on an Apple M2 using HV acceleration. HV acceleration means it's the same thing as KVM, right? Your code executes on the host CPU. There is no emulation there. So you're running really on the M2 processor, even though you're running on top of QEMU. And what I saw was nothing, right? The performance looked exactly the same, which means that at least when you run on top of a VMN, then the overhead is non-perceivable. Of course, if you run directly bare metal, you should be able to see like even these few instructions overhead, but not on the VVM. So it's masked most probably by the noise of OS entry, OS exit, and all these things, which is, of course, fantastic. Finally, the last metric was the code size. How much do these extra instructions grow our image and, of course, our memory footprint? And ARM claimed some very small numbers. Long story short, I did something similar, and again, ARM's numbers seem credible, right? So you have something like, I don't know, even less than 2% growth in the image size, which again is very good. So, in practice, are now CFI attacks over? And the answer, as you can guess, is no, right? So, actually there is a lot of interesting reads on this. Pacman is a side channel attack, which means that they managed to break Pointer Authentication and BTI via side channels. If I remember correctly, ARM already introduced an extension that addresses this. All the rest are workarounds. Or, I think one of the first ones was a buggy implementation in the XNU kernel of Apple, right? They did something buggy and people could then reuse, I think, sign pointer or something like that. So all the rest is workarounds. So does it mean that these protections are broken? By no means, right? It's very hard to attack Pointer Authentication and BTI. Normally people work around them, and then you have also new protections coming in, like MTE in particular, that will make exploitation even harder. Okay, so in conclusion, so Pointer Authentication and BTI are performant and they're effective. They're great value for money because the implementation effort for the improvement ratio is very good, right? They're pragmatic. You don't need to rewrite code, like how people, I don't know, propose, I don't know, rewrite everything in Rust and etc. Right? You only need small implementation changes in the kernel to enable the feature, and overall, it's a very big step forward compared to software mitigations. Eventually, also, they will be present in every ARM-based system on chip. And even though they have been proven actually not possible to, well, not impossible to bypass, they're still, let's say, a big improvement because they make exploitation significantly harder. As I said, there are more mitigations on the way, especially MTE, which I think addresses the problem of memory safety at its core because it detects memory violations when they happen. And of course, there is also Cherry that is based on fat pointers with capabilities. That is something very promising for the future. Okay, so I'm done. Thank you very much. And if there are any questions, I'll be more than happy to answer.
What about the compilation time?
Cool. So the question is, what about the compile time? The answer is, I don't know. I have not measured it because normally compile time is cheap. You don't care about compile time. What you care about is runtime, right? For compile time, you have even like entire servers to do the build for you, but I don't expect to see any significant also increase, like penalty in the compile time. Yes?
For PAuth, and where did the process key store at? Is it stored in the user space or kernel space, and is it stored in the register or what? Is it appear somewhere in the memory state?
Okay, so the question is, when we do the process switch, where are the process keys stored, right? And these are stored in memory in the kernel space.
Kernel space.
Yes, of course, because the kernel will save the context of every process, right? Anyway, so now you have additionally the contents of the key register to store on the kernel. And then when you do the context switch, the same way how you restore the context of the process, you also have to additionally restore the keys. Okay, I think I have no more questions, so thank you very much.
That's the end of all sessions in M.T1, and thank you Michaelis Papas for a wonderful sharing. To those who are interested in lightning talk, just feel free to go to M.T2 and it will start at 4:30. And remember to join the lucky draw about JetBrains license after the lightning talk.